Welcome to AI Frontiers, where we explore the cutting-edge research that's reshaping our understanding of artificial intelligence. Today, we're diving into machine learning breakthroughs from September 11, 2025. These papers represent the blueprints for tomorrow's AI systems, covering neural network optimization, fairness in AI, scientific computing applications, graph-based learning innovations, and few-shot learning advances that will transform how we interact with artificial intelligence. Picture this. You're scrolling through your phone, and an AI system instantly recognizes your voice, translates your words into another language, recommends the perfect restaurant based on your mood, and even predicts what you'll want to watch tonight. All of this happens in milliseconds, powered by algorithms that are learning and adapting faster than ever before. But here's the surprising part. The very systems making these predictions often can't explain why they made them, even when we ask them directly. It's like having a brilliant friend who always gives great advice but can't tell you how they came up with it. This paradox defines our current AI landscape, where systems become increasingly powerful, yet remain mysteriously opaque. The invisible engine of our digital world operates behind the scenes in search engines, social media feeds, and countless applications we use daily. Today's research papers hold tomorrow's blueprints, revealing how these mysterious systems will evolve to become even more integrated into our lives. Welcome to the learning revolution, where algorithms adapt faster than ever before. Machine learning has become the driving force behind everything from medical diagnoses to climate predictions, from financial trading to molecular discovery. Unlike traditional programming that follows rigid rules, machine learning teaches computers to learn from experience, much like how we humans acquire knowledge. Today we're examining 41 groundbreaking papers from September 11, 2025, all emerging from this dynamic field that's reshaping our understanding of artificial intelligence. These aren't just academic exercises. They represent real-world solutions that will impact healthcare, environmental science, urban planning, and countless other domains. The research we're exploring today bridges the gap between academic theory and practical applications, showing how machine learning continues to evolve from laboratory curiosity to essential technology that powers our modern world. Think of machine learning as the brain of modern artificial intelligence. It's the field that teaches computers to learn from experience rather than following rigid programming rules. Just as a child learns to recognize faces by seeing thousands of examples, machine learning algorithms improve their performance by processing vast amounts of data and finding patterns that humans might never notice. This field sits at the fascinating intersection of mathematics, computer science, and human psychology, borrowing statistical techniques from mathematics, computational power from computer science, and insights about learning from cognitive science. What makes it particularly exciting is how it bridges pure theory with practical problem solving, creating systems that can adapt to new situations and make decisions in complex, uncertain environments. Machine learning has become the invisible engine driving our digital world, operating behind the scenes in search engines, social media feeds, autonomous vehicles, and countless other applications we interact with daily. Our first major theme focuses on neural network optimization and efficiency. Imagine trying to fit a massive library into a smartphone. Researchers are developing ingenious ways to compress powerful AI models without losing their capabilities, making advanced AI accessible to everyone, not just those with supercomputers. The ButterflyQuant paper introduces learnable transforms that dramatically reduce the memory needed to run large language models, potentially bringing ChatGPT-level capabilities to your laptop. This breakthrough achieved a perplexity score of 15.4 compared to 22.1 for previous methods when compressing language models to just 2 bits per parameter. To put this in perspective, that's like compressing a 100-gigabyte model down to just 6 gigabytes while maintaining most of its intelligence, a game-changer for bringing powerful AI to everyday devices. This optimization revolution challenges the assumption that bigger is always better in AI, instead focusing on making existing models dramatically more efficient through clever mathematical insights and adaptive optimization approaches. The second theme focuses on fairness and robustness. Think of it as building AI systems with a moral compass and bulletproof vest. As AI makes increasingly important decisions about healthcare, lending, and criminal justice, researchers are working to ensure these systems treat everyone fairly and can't be fooled by malicious attacks. This isn't just about technical performance, it's about social responsibility and trust. One study addresses healthcare disparities in Medicaid programs, while another tackles the challenge of training AI models across multiple organizations without compromising data privacy. The fairness challenge becomes particularly complex when we consider that AI systems often reflect the biases present in their training data. Researchers are developing new techniques to detect and mitigate these biases while maintaining system performance. Robustness research focuses on making AI systems resistant to adversarial attacks, malicious attempts to fool the system into making wrong decisions. This is crucial as AI systems become more prevalent in security-sensitive applications. Our third theme explores scientific computing applications. Imagine AI as a universal translator between different scientific languages. Machine learning is becoming an indispensable tool for everything from predicting urban water dynamics to discovering new molecules for drug development. These applications require not just high performance, but also deep integration with scientific principles and domain expertise. One remarkable finding shows a 30% improvement in soil mapping accuracy when spatial knowledge is integrated with machine learning approaches. This demonstrates how combining AI with domain expertise can yield remarkable results that neither approach could achieve alone. From climate modeling to transportation networks, from molecular structures to ecological systems, AI is helping scientists understand complex phenomena that would be impossible to analyze using traditional methods. The key insight is that successful scientific AI applications require deep collaboration between machine learning experts and domain scientists. The breakthrough discoveries from our research collection reveal truly groundbreaking results. The most impressive achievement comes from the AEGIS system, which reached 100% recall and 99.4% accuracy in automatically processing academic papers, essentially creating an AI librarian that never misses a relevant document and rarely makes mistakes. This level of performance suggests that AI agents are ready to handle complex real-world information processing tasks that previously required human expertise. In molecular discovery, researchers achieved a 15.3% improvement in generating molecules with specific desired properties, dramatically improving our ability to design new medicines or materials by computer simulation before expensive laboratory testing. The Rabano framework achieved discretization invariance, creating AI models that perform consistently whether running on smartphones or supercomputers. This reliability breakthrough is like having a GPS that works equally well with detailed city maps or rough sketches, providing consistent performance across different computational environments. Now let's dive deep into our paper of the day, ButterflyQuant, which tackles one of the most pressing challenges in modern AI. Imagine you have a brilliant friend who knows everything about everything, but they speak so fast and use such complex language that you need a supercomputer just to have a conversation with them. That's essentially the problem with large language models today. They're incredibly capable, but require enormous amounts of memory and processing power. The researchers behind ButterflyQuant asked a deceptively simple question. What if we could teach these models to communicate more efficiently, without losing their intelligence? Their solution involves learnable butterfly transforms that adapt to the specific characteristics of each layer in the neural network, rather than using a one-size-fits-all approach. This breakthrough makes genius-level AI accessible to everyone, not just those with massive computing resources, fundamentally democratizing access to advanced AI capabilities. The technical breakthrough of ButterflyQuant lies in recognizing that different parts of neural networks have different patterns of information storage. Think of these as smart compression algorithms that adapt to each layer's unique characteristics, like having a personalized filing system for each room in a massive library. The key insight was that neural network layers exhibit distinct outlier patterns. Some layers have a few neurons that are extremely important, while others distribute importance more evenly. Previous methods treated all layers the same way, like using the same organizational system for both a poetry section and a technical manual section. ButterflyQuant instead learns custom organizational systems for each layer, dramatically improving efficiency. The butterfly structure provides a mathematically beautiful way to maintain essential properties while enabling smooth optimization using continuous methods rather than trial and error approaches. This elegant solution bridges several areas of mathematics and computer science, from matrix theory to optimization algorithms. The experimental results from ButterflyQuant were remarkable and game-changing. When researchers compressed the LLAMA-2-7B model, a state-of-the-art language model with 7 billion parameters, down to just 2 bits per parameter, their method achieved significantly better performance than previous approaches. Most importantly, this compression was achieved using only 128 example sentences and converged in just minutes on a single GPU. This efficiency makes the technology accessible to researchers and developers who don't have access to massive computing clusters. The implications extend far beyond academic research. This could enable powerful AI assistants to run on smartphones, laptops, and other consumer devices. Rather than pursuing ever larger models that only a few organizations can afford, this research represents a shift towards sustainable AI development that considers performance, accessibility, and environmental impact. The success challenges the assumption that bigger is always better, showing we can make existing models dramatically more efficient. Looking toward the future, ButterflyQuant opens exciting possibilities for the next generation of AI systems. We're likely to see a new wave of efficient, accessible AI tools that can run on everyday devices while maintaining the capabilities we've come to expect from cloud-based systems. Imagine having a personal AI tutor on your smartphone that's as knowledgeable as today's most advanced chatbots or real-time language translation that works without an internet connection. The techniques could inspire advances in other areas of AI compression and optimization, with adaptive, layer-specific optimization applying to image recognition systems, scientific computing applications, and autonomous vehicle control. This research represents a maturation toward more sustainable and inclusive AI development, enabling smaller organizations and developing countries to participate more fully in the AI revolution. The success of learnable, adaptive approaches suggests the future lies not in finding single best solutions, but in developing systems that automatically adapt to each problem's specific characteristics, a meta-learning approach where systems learn how to learn more efficiently. As we wrap up our journey through today's machine learning frontiers, we're witnessing a field in remarkable transition. The 6 themes we explored, efficiency, fairness, interpretability, scientific application, graph-based learning, and few-shot learning, represent the current pulse of a field balancing theoretical rigor with practical impact. From quantum-inspired optimization techniques that make powerful AI accessible on everyday devices, to fairness-aware algorithms ensuring equitable healthcare delivery, to interpretable models explaining their reasoning in scientific terms, these advances reshape not just how we build AI systems, but how they integrate into society's fabric. The breakthrough findings demonstrate machine learning moving beyond proof of concept toward reliable, deployable solutions for real-world challenges. Most encouragingly, we're seeing a shift toward more sustainable, inclusive, and explainable AI development. These systems won't just change how computers work. They'll change how we work with computers, becoming partners in scientific discovery, assistants in creative endeavors, and tools for tackling humanity's greatest challenges. This research summary was created using advanced AI synthesis techniques to bring you the latest developments in machine learning. The content synthesis utilized GPT and Claude SONNET-4-20250-514 models to analyze and summarize the original research papers. Text-to-speech synthesis was powered by DeepGram's advanced neural voice technology, while image generation utilized OpenAI systems to create relevant visual content. All synthesized content underwent human expert review to ensure accuracy and clarity. We provide references to original papers when available, though we acknowledge potential oversights in our automated analysis. This hybrid approach combines the efficiency of AI processing with human oversight to deliver comprehensive coverage of cutting-edge research. We encourage listeners to explore the original papers themselves, as many are freely available through the archive preprint server and other academic repositories. Thank you for joining us on AI Frontiers today. I encourage you to dig deeper into these papers yourself. Many are freely available online, and the insights they contain will shape the technology landscape for years to come. Share your thoughts about which applications excite you most, or which challenges concern you on social media, using the hashtag AI Frontiers. The future of artificial intelligence isn't just being written by researchers in labs, it's being shaped by all of us who will live with and benefit from these remarkable advances. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses archivepreprintserver.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by archivepreprintserver.org.